Yeah, I guess I'll get started. Thanks a lot for having me over, and apologies for not being able to be there in person due to some visa constraints. So thanks for the organizers to allow me to do this remotely. Um, so yeah, today I want to talk a bit about understanding human-object interaction and how that can be a pathway for enabling sort of generalizable robot manipulation. And so yeah, and so I think maybe when I was growing up as a kid, and a lot of us were growing up, we always had these robots in sort of cartoons and sci-fi, and this was always the promised future or the promise of robotics, that at some point we will hopefully have these robots that can be in our homes and do a lot of things for us, right? And more firmly, there's always been this dream or this promise of being able to develop generalist robots that accomplish many tasks. So there's a single robot that can accomplish many tasks, and it can do this across diverse environments. In the sense, if I buy a robot butler, it should be able to work in my home, it should be able to work in my neighbor's home, your home, and so on. And while that is the eventual, sorry, now there's some, okay. And while this is the eventual goal or dream in robotics, the sort of current reality is a bit further from this. And we've had a lot of really impressive systems developed in robotics. For instance, there was this very impressive result from OpenAI a few years back where they had a dexterous hand that was solving Rubik's cubes. More recently, we've seen results from sort of Google and Stanford, etc., where there are robots that can tie shoelaces or put t-shirts on hangers, etc. And again, I want to emphasize that these are really, really impressive systems. A few years back, we could only do things like these in simulation. And the fact that now we have real world systems that can accomplish these dexterous tasks is really amazing. That said, this is still a far cry from this promised future of this generalist robot, because these are really task-specific policies that can't even handle a lot of object or scene variation. For instance, the OpenAI robot can only solve this specific Rubik's Cube. The sort of shoe tying robot or the sort of shirt hanging robot can only hang this specific kind of a t-shirt. So if you give it a t-shirt without a collar, this policy that we've learned probably won't work. Okay. And so one natural question to ask is, why is this gap? What is holding us what is holding us back? Why is the current reality not really matching sort of this promise of this generalist robot? And sort of one part of the answer, at least, is that there is this strong data dependency on interaction data for sort of learning manipulation systems. I mean, learning manipulation is hard. And if we apply our current techniques for machine learning, they just require a lot of data to be able to train. Sort of as an example, this sort of Google dexterous robot requires about, on average, 10K demonstrations per task. So we've shown it 10K human demonstrations of tying shoelaces. We've shown it about 10K demonstrations of hanging these kinds of t-shirts with this kind of a collar. And only then can it learn to do this at, let's say, 60-70% accuracy. Sort of the OpenAI system required about 13,000 years of interactions in simulation, which isn't quite free in the sense it required 64 GPUs running for over 6 months. And so that's sort of a lot of compute, and it's not very easy to scale, right? And so towards this promise of this generalist robot, one natural question is, okay, if there is this bottleneck, how do we solve this? How do we get towards these more generic systems? And perhaps the first answer any of us might have is, well, that's fine. Like, if we need more data, let's just collect much more data. And in fact, that's a perfectly valid answer. And there are sort of entire companies betting on this as being sort of the answer, in the sense Tesla is developing its humanoid robots. There are positions that are now cropping up for these people to train these humanoid robots by teleoperation. It's sort of called this humanoid robot operator, robot trainer. There are these specialized jobs that are cropping up all over the place. And a lot of companies are betting big that if we just collect a lot more robot data, things will at some point start working. And sort of that's a perfectly reasonable sort of hypothesis, except I would still argue that this is not a very easy thing to scale, right? We require sort of these humans to be able to there is no readily available internet data of robot interactions, and we need these relatively costly teleoperations that are not as easy to scale. And in fact, the scaling laws may apply differently to the laws of scaling for, let's say, video generation or image generation. If you're generating an image of sort of cleaning a dish, it's okay if there's something inaccurate. But if your robot is trying to clean a dish and it sort of does a bad job, it will just break the dish. So we have a much higher robustness and performance bar, and we probably might have different scaling laws for this, right? And so one question that we've been asking is, while scaling this robot data collection is going to be a bit difficult, is there a more scalable source of data that we can still use for learning robot manipulation? And in fact, there is a lot of data for generalists agents that exist in the world and do a lot of everyday tasks. There are generalist agents that act in the world, do things like sort of cooking, cleaning, etc. And that's us humans. And we have a lot of data available showing humans interacting with the world around them, performing everyday tasks. We sort of there are a growing number of ecocentric data sets. This image is from a data set David Foy et al. Collected a few years back. But since then, there have been many, many more data sets showing just humans interacting with the world. And so given that there is this readily available interaction data, just of a different morphology, the hope is that we can use this somehow to benefit robot manipulation. And this is not robot data. This is sort of third person of data of a different individual interacting with the world. But we humans learn by watching others. Animals also learn by watching others. So it's not that much of a leap to ask robots to also learn by watching others. And so here's maybe one alternate recipe for trying to build generalist robots, which is one, we need systems that can understand all of this rich data on the internet showing a myriad human interactions. And once we have some sort of an understanding, and this understanding will need to sort of understand motions, 3D physics, etc. Given this sort of an understanding, we want to develop manipulation systems that are guided by this understanding of, or this large-scale data of humans interacting with the world and affecting it. And today I want to show you a couple of projects along these lines. So one, this is actually a paper that my student Humanga will be presenting at ECCV. So please feel free to go to his poster if you want to see more details, where we've shown some results where we learn generalizable policies that can accomplish multiple tasks using a lot of human interaction data as a supervisory signal. And this work, however, does relatively simple actions. And so, to allow these systems to perform more complex tasks in the future, we've been looking at understanding dexterous hand-object interactions and being able to reconstruct and learn priors over them. And this is sort of a work that we presented at CVPR. Okay. So yeah, I'll go into some details on both of these. And so first, starting out with the manipulation task, the goal here is to learn some kind of a generalizable interaction policy, right? So when I say a generalizable interaction policy, what I mean is we want a policy that can take some observation, that this is how my environment is currently. It takes some goal specification. So in this work, we use a goal image. In a work that we just archived, we actually use a language specification. So there's some goal specification. And you want a policy that just executes this task. So given this observation and some goal description, it can just achieve that goal. And we want a generalizable policy that can achieve arbitrary goals across diverse environments. So all the three interactions that you're seeing on the left have different kinds of motions, different kinds of objects, and all of those are achieved by a common policy that has been sort of that can achieve any of these things across new environments. And of course, we are not the first to try to learn such a policy. Maybe one of the most prominent examples of learning such a policy in recent times is this RTX line of work from Google, sort of RT1, RT2, etc., where they learn a similar policy that can accomplish many different language-specified tasks, except that they require about sort of 13 months of data across different demonstrations to be able to train such a policy. And even then, there is limited generalization to new skills and object categories. So for instance, if this policy never saw a microwave in robot training data and you ask it to open a microwave, it cannot accomplish that task. Whereas we are hoping for a more generalizable system that can work across new environments and perhaps even new object categories. And so the system that I'll talk to you about can actually be trained with just 500 demonstrations across all tasks, compared to what two orders of magnitude more demonstrations. But it uses about 1 million human interaction clips from the internet as sort of a pre-training. And as I'll show, this system can even allow us to generalize to new skills and object categories that the robot has never seen. These are things that we've already seen in the human data, but never in the robot data. Okay. And the key design decision here is that when we are learning this policy, we have a factorized representation of this policy. So one, given a image and a goal specification, we try to have an interaction plan, which is how should my interaction proceed? How should the world change over the course of the interaction? And this is something we can learn using large web data of human interactions. And this has nothing to do with sort of robot specific data. And then given this predicted interaction plan, we can actually even plan a motion that the robot should directly execute, or we can learn policies using a small amount of robot specific data, such as 500 demonstrations across sort of different kinds of tasks. And so the interaction plan that we learn in this work more specifically is a point track prediction network, and it's a sort of diffusion-based model, so it does probabilistic point track prediction. Again, using these about 1 million clips on the internet, we use any off-the-shelf point tracker. So here, I think we were using the system called Co-Tracker from Meta AI, where it can just easily give us 2D pixel tracks of things that are moving in the video. Given this, we can just learn a system that, given an initial image and a final image, predicts how pixels will move between the final image and the goal image. So here you're seeing that the model understands that the pixels on this book should move in a certain way, and so the other pixels should not really. And it's the way we train this model is as a denoising diffusion model. So it requires an initial image and a goal image and this diffusion time step. It also takes in sort of noisy point tracks. So it's a diffusion model, so it learns to denoise noisy point tracks. So we have a few randomly sampled pixels and their noisy point tracks. And this diffusion model basically denoises these tracks by some self-attention across these tracks and some cross-attention to the sort of initial and goal image. And I'll point you to the paper or ask you to go to Among Us poster for more details. But at a high level, it's just this denoising diffusion model that can predict these denoised pixel tracks given an initial image and goal image. And so what this allows us to do using about sort of 1 million internet clips is learn this track prediction model that, given any two images, can give us pixel tracks of how things in the image should move to achieve the goal. And then using these, we use this to plan out how a robot should act. So if you assume that you know the depth of the scene, which we often do in robotics deployment settings, we can compute a rigid transform that best explains the 2D motions that we have observed. And we can plan the robot motion to essentially follow that rigid transform. But we never execute this open loop plan. We learn a residual policy that corrects this plan. And this residual policy we learn using a small number of demonstrations, as I said, about 500 demonstrations across a lot of tasks. And this gives us a very efficient and generalizable way of being able to do different tasks. And here's sort of a glimpse of the results, where we have a single policy that is going to be performing all of these actions sort of given the corresponding goal. So it can open waffle makers, do this pouring action, open drawers, pick and place objects, close drawers, sort of open hinge doors, etc., etc. And there's this single policy trained using just 500 robot demonstrations that is accomplishing all of these tasks. And one thing I want to emphasize is that we spent a bit of time trying to characterize generalization in a meaningful way, in the sense our robot data only has a small number of demonstrations. So we can systematically hold out objects or systematically hold out kind of skills that we are showing to the robot and characterize generalization as, hey, have we already seen this specific object and seen this specific skill? Have we seen similar objects, but not this specific instance, and so on. And maybe the strongest one is type generalization, where we haven't even seen that category in robot data. Again, everything has been seen in human data, but not in robot training data. And so here are, and maybe I'll sort of skip, the high level takeaway is that even if you do naive behavior cloning, things work reasonably well in mild generalization, which is you've already seen these instances in your training data, and you've just shuffled their position or changed lighting in the scene. But as we go towards stronger generalization settings, this human data-based prediction model becomes really, really useful. And so here are some examples of this type generalization. So a robot has never seen books or chairs and microwaves in its robot training data, and still it can accomplish these goals like, still it can accomplish these goals like pulling the chair to the left, closing the microwave door, or picking up the book. And there are other kinds of generalizations. So this robot has never seen this combination of this category and this skill. So it has seen cloths, but it has never sort of wiped things with cloths, and can kind of do that reasonably well. And then there are more normal kinds of generalization where it's new instances of seen categories or seen instances of seen categories. And it doesn't sort of always work. Often it does fail. Sometimes it does fail to grasp the object, and then subsequent motion obviously fails. But it works pretty reasonably. And given the fact that we can train the system using a very small number of demonstrations, this is still quite remarkable that it does all the tasks that I mentioned earlier. And here's maybe just a showcase of us using this robot in a few everyday environments where we are teleoperating the robot for navigation, but then it autonomously performs the manipulation. So you have pre-specified the goals for it. And so it can go to this, we can take it to this place, and then it will pick up the book and keep it somewhere. And then we'll take it somewhere else. It has a different pre-specified goal, which sort of it will execute. So I think we pre-specified the goal that it should open this specific drawer, and it can sort of just do that. So you can very easily see how this sort of a generalizable policy, where there is a single policy that can accomplish different kinds of goals, can be very useful in our everyday environments. And yeah, we sort of make it go around and open a few more things, which I'll maybe skip in the interest of time. And so this really, for me, is an example of this generalizable manipulation system that can be learned by crucially relying on a lot of human interaction data. In this specific case, we extracted tracks or performed track prediction and used that as a stepping stone for generalizable manipulation. The obvious limitation here is that this is restricted to relatively simple non-dexterous tasks, right? Things like pick and place or opening things which don't really require dexterity or don't really require sort of use of these multi-fingered hands. And in the future, as dexterous robots are becoming ever more popular, we want to be able to scale such systems to be able to learn from dexterous videos of humans interacting on the web. And so with that, we've been looking at how do we enable understanding of dexterous interactions from internet videos, in particular being able to reconstruct and generate hand-object interactions. And so maybe the typical problem statement in this line of work is we'll get this input video. Again, just think of a random arbitrary YouTube clip of a few seconds of a human interacting with some object. And we want to be able to perform 3D reconstruction, understand what happened, what the object was, where the contacts were, what happened in this sort of particular interaction. Okay. And of course, this is an extremely challenging task. Like everyday clips that you see often have a lot of occlusion. Your hand is often occluding the object. You see very limited viewpoints of the object. So for instance, this knife, even though it's a video, you don't really see the other side of the knife. You observe only a very limited viewpoint of this object. And so this makes it a very challenging task. And the initial few approaches for this task actually typically assumed that we know the 3D object, and we're just estimating its 60 pose in each frame. But of course, this is perhaps not the nicest system to use, because for every new YouTube clip, you want someone to be able to annotate what is the template that corresponds to this object. And so, while these can give you pretty impressive results, they're perhaps not the most user-friendly. And so there have been several methods that try to learn in a template-free manner. I think some works from our group, some other works from other labs around the world, where you can learn, let's say, single view prediction. So given per frame of the video, these are systems that can predict the 3D hand in the object. But of course, because these are per frame prediction methods, they don't use temporal consistency, they don't use multi-view consistency. And it's sort of pretty impressive that they can estimate this from a single frame. But of course, this is not a very nice and accurate reconstruction of the underlying interaction. On the other hand, there have been other methods that actually just frame this as a multi-view reconstruction task, that in a video, we observe multiple views of the hand and the object, and we just want to reconstruct these, sort of building on nerves, etc. But of course, they fail when you only have limited viewpoints. So these are great for enhanced scanning setups, but they sort of assume that you'll observe all aspects of the object. And so in our group, we've been looking at trying to combine both data-driven priors and multi-view signals. So in particular, given an input clip, we still optimize a per scene representation. Sorry, was that? Okay, we still optimize a per scene representation, that what is the 3D interaction that's going on and what are the underlying cameras, using multi-view reprojection error, but also using 3D data priors. And so I'll focus a bit more on sort of the data prior, which is perhaps the more interesting part here. And the specific data prior that we learn is this 3D generative model that produces a hand object interaction using this, what we call an interaction grid. So this interaction grid encodes both the 3D shape of the object as a sign distance function, and it encodes the hand configuration relative to the object. And I think here is maybe one of the technical details that turned out to be really important, which is that typically we parameterize hand articulation by just these numbers, theta, sort of the joint angles, etc. But it turns out to learn this 3D diffusion model, we really needed a 3D representation of the hand articulation. So we defined this skeletal distance field, which tells us how far each voxel is from each of the hand joints. And so this gives us this volumetric representation of the hand articulation, which can be concatenated with volumetric representation of the object. And then we learn a 3D diffusion model that can sort of predict this interaction grid, and then we can recover the object 3D as well as the hand articulation using this. And actually, a bit of the time in this project was just spent in engineering efforts and collating all of these very different data sets into a similar format so that we could use these all for training. And this using all these different data sets gave us about 157 categories with this nice long tail distribution. So this is a diffusion model that has seen lots of different kinds of hand object interactions for a lot of different kinds of categories. And once you've trained this data prior, we can just ask it to generate plausible interactions. So we can ask it for sort of a hand holding a power drill and sample it, and it will give us different object shapes, and it will give us different hand articulations with respect to the object. You can ask it to generate sort of spray bottles, lids, teapots, etc. And it gives you samples of both shapes and the hand interacting with that shape. And so this is this nice generic prior that has learned the distribution of different hand object interactions. And then we can use it for the tasks that we were initially interested in, which is we can use it to reconstruct interaction videos, and we can actually also use it to synthesize grasps. And I'll maybe briefly go over this. So given sort of a video, we optimize a 3D representation of this particular interaction. What that means is we have an SDF representation for the object, a per time step articulation for the hand, and the time varying transformations between the two. And we say that, hey, this representation should be likely under our data prior. And given the cameras that we're also predicting, it should explain the video, or it should reproject in the right way with respect to the video that we're observing. And so this combination allows us to perform reconstruction of these clips. And DIF HOI was a previous work from a group that used sort of a 2D generative prior. And here, using a 3D generative prior, we get much faster and much better reconstructions, which is sort of the GHOP column in between is the result of this framework that I just talked about. And I'll maybe skip some of these evaluations in sort of interest of time. But I think one point I want to highlight is that the difference between the light blue curve and the dark blue curve is if you learn a conditional 3D model of the object versus if you learn a joint model over hand and object together. So learning a joint prior actually allows us to infer much better hand reconstruction compared to a model that is only predicting or learning a diffusion model on the 3D object given the hand. And we can also use this model, now that it has a hand prior, to synthesize plausible grasps given a 3D shape. So basically, given a 3D shape like a banana, we can sort of optimize a relative transformation between the object and the hand articulation, again, by just saying that, hey, this interaction should be likely under our data-driven prior. And given an object, we can synthesize much more plausible grasps compared to previous work. And in fact, our grasps have contact in the right location, like the palm and the front of the fingers, whereas prior work often also gives you contact at the back of the hand, for instance. And we also did a user study to sort of show that our synthesized graphs are much more accurate. But we can also not only sample multiple graphs, we can also rank them using the likelihood under our model. And so we see that the model knows that a power drill should be grasped in this specific way, as opposed to from the bottom of it. And yeah, here are just some more results from our system, where you can take a YouTube clip of maybe a human hand interacting with a generic rigid object and give that to a system, and it can give you a plausible reconstruction of it. Or you can give it a mesh and it can generate multiple plausible grasps of how a human hand would interact with this. And yeah, I would encourage you to go look at more details of this project on our project website. But I think kind of just want to wrap up again with this big picture that there is currently this gap between perhaps where we want to be in terms of developing these generalist robots and what we can currently do, which is train these really impressive but task-specific systems. And I think for me, the hope really is that understanding hand-object interactions on the web can help bridge this gap. So for instance, if you're someone who's working on robotics, perhaps you can look at all the excellent work that you will see in this particular workshop and think about how that can be useful to you. Or if you're someone who's working on hand-object interactions, I would like to nudge you to also consider robotics as one particular application and try to show off the kind of systems that you build and show that they really help some robotic systems downstream. And yeah, with that, I'd like to end and thank my collaborators, in particular, Judy and Humanga, who led all of the work, and Abhinav, Chris, and Rusbe, whose names are unfortunately switched. And so maybe I'll fix that, who sort of were great collaborators throughout this. And yeah, I'm happy to take any questions if there are.